You know, for the longest time, quantum computing has sounded like something straight out of science fiction. But what if I told you that this revolutionary technology is rapidly moving from theory to reality? So what is it really? And why is it about to change everything? Let's dive in. Just let that sink in for a second. There are problems in medicine, in finance, in creating new materials that are so ridiculously complex that even the beefiest supercomputers we have today would take literally billions of years to solve them. Quantum computing isn't about making a faster iPhone. It's about building a completely new kind of machine to solve the impossible. And this quote just nails it. It perfectly captures this moment we're in. All those weird, mind-bending, spooky ideas from quantum physics are finally leaving the chalkboard and becoming actual, tangible hardware, powerful tools we can use in the real world. Okay, but before we get into the nuts and bolts of how it all works, we've got to clear the air a little bit. We need to get beyond the hype and talk about what this stuff actually is and isn't.
So, let's get one thing straight right off the bat. A quantum computer is not going to replace the laptop or phone you're watching this on. Nope, think of it more like a specialized tool, a superpowered coprocessor designed to work alongside our regular computers to tackle a very specific set of problems that are, for now, completely out of our reach.
So what's the secret sauce here? What makes a quantum computer so different? Well, it all comes down to harnessing the wonderfully strange, almost magical rules of the quantum world. And this is where things get a little spooky. All right, so your regular computer uses bits, which are always either a 0 or a 1. Simple. But quantum computers use qubits, and thanks to a wild idea called superposition, a qubit can be a 0, a 1, or kind of both at the exact same time. It's just like the famous thought experiment with Schrödinger's cat. The cat is both alive and dead inside the box until the moment you look. This ability to explore many possibilities at once is what gives quantum computers their incredible power. And then there's the second key ingredient, and this one's even weirder. It's called entanglement. This is where you can link two qubits together so that their fates are intertwined. Whatever happens to one instantly, and I mean instantly, affects the other, even if they're on opposite sides of the galaxy.
And get this idea was so bizarre, so counterintuitive, that it even freaked out Albert Einstein. He famously called it spooky action at a distance. It's just incredible to think that this puzzle that baffled the greatest minds is now one of the core building blocks of this new technology.
So, okay, that's the mind-bending theory. But how in the world do you take these concepts and actually build a working machine? Well, that's the journey we're on right now, from the lab to reality.
And the progress is happening at a blistering pace. The hardware is improving like crazy. Look at this. We're not just cramming in more qubits anymore. These new processors are designed to handle thousands of complex operations, and more importantly, they have more connections between the qubits. That connectivity is absolutely crucial if you want to solve real, useful problems. But for all this amazing progress, there's always been this one giant, massive roadblock. Qubits are unbelievably fragile. The slightest little disturbance, a tiny change in temperature, a stray magnetic field, can knock them out of their quantum state and create an error. And for years, this error problem has been the big, seemingly impossible mountain to climb.
But that's starting to change. A huge breakthrough recently came into focus, and it centers on this number, 448. So why is that number so important?
Well, a team at Harvard just built a system with 448 qubits that can do something that's never really been done at this scale before. It doesn't just compute, it can actively detect and correct its own errors while it's running. This is a game changer. It's the first real proof that building a big, scalable, error-tolerant quantum computer isn't just a fantasy, it's an engineering problem we are now actively solving.
And look at this timeline. It is accelerating. IBM is publicly targeting 2026 for something they call quantum advantage. That's the tipping point, the moment a quantum computer solves a useful problem better than any classical supercomputer on Earth could. And by 2029, the goal is a full-scale, fault-tolerant machine. This isn't science fiction anymore. This is happening now. So, we're building these incredible machines. What are we actually going to do with them? Well, one of the very first and maybe most profound applications is set to be a complete revolution in medicine, specifically how we discover new drugs. Let's just stop and ask a simple question. Why does it take over a decade and literally billions of dollars just to bring one new drug to the market? A huge piece of the puzzle comes down to a massive computational bottleneck. This table basically lays out the whole problem. To really truly understand how a drug molecule will work in the body, you have to simulate its quantum behavior. But trying to do that on a regular computer is basically impossible for any molecule that's even a little bit complex. The computing cost just explodes. So scientists have to cut corners and use approximations, which means they're sacrificing accuracy for speed. And that's a big reason so many promising drugs fail.
And here is the paradigm shift. This is the whole ballgame. A classical computer struggles because it's faking it. It's approximating a quantum system. But a quantum computer, it speaks the native language of molecules. You're not approximating anymore. You're using a quantum system to simulate a quantum system. It's the perfect tool for the job.
So this new capability, it really does mark the dawn of a new era. As these incredible machines come online, what does the future of computing actually look like?
Well, the future isn't quantum versus classical. It's quantum and classical working together as a team. Think of it like this. The classical computer is the team captain. It handles all the normal stuff, the inputs, the outputs, but for that one ridiculously hard calculation right at the heart of the problem, like figuring out a molecular bond, it hands the ball off to its superstar player, the quantum core, to do the heavy lifting.
And the impact is going to spread way beyond medicine. I mean, imagine designing brand new materials, atom by atom, to create things like hyper-efficient batteries or solar panels, or building financial models that can actually predict risk in chaotic markets, or even supercharging artificial intelligence. The possibilities here are just staggering.
And you know, this brings us all the way back to a vision that the great physicist Richard Feynman had way back in 1981. He realized that nature is quantum, so if we ever wanted to truly simulate it, we'd need to build a quantum computer. What was once just a brilliant futuristic dream is now taking shape right in front of us. We're building a new tool not just to calculate things, but to understand the very fabric of reality itself. The question is no longer if this will change our world, but how profoundly, and how soon.